I will talk about our product that is called myGym, and it's in its version of 2.1, and it is dedicated to training neural networks capable to do the motoric tasks and do it safely. And as I said, we are a group dedicated to, or stemming from cognitive science. We mostly worked with the combination of vision and language. That means something for representing meaning, because we do believe that it's better to learn the meaning compared to pre-programming it. And in the area of language description of the scenes on the table, we were able to train the networks to be pretty capable to, let's say, describe what's going on a table, what are relations, and about the static objects. But then we moved to an area, because I mean the language output is nice. I mean, when somebody talks to you, the answer is good. But if you are capable to do something, and you are able to understand not just the static world but also the dynamic world, we need to move to these simulators and be capable or train the networks that are capable to recognize the actions and able to do the action, because this is like a next step of understanding the meaning. And at the end of this, there are systems that are capable to represent actions in some similarity measures. I mean that if you are unable to do this one action, you have a similar action that is pre-trained, and you can create a sequences of action. This is like a goal also in artificial intelligence and in robotics. I mean, to have a system that you will give the actual state, then a goal state, and the robot itself is able to sequence the actions and to fulfill some task, let's say assembly one. So this is the motivation behind. When we start with the simulators, we mostly found, I mean, it's a first one is usually is like OpenAI Gym. That is a standard how to create the artificial environment. It starts with the Atari games. I mean, mostly the discrete worlds, like a grid world. And when you move to a continuous world, let's say robotics, it starts to become difficult, because you need or the tasks are, the complexity and the difficultiness of the level task grows, but the previous toolbox that are mentioned in a table, it was always difficult for us to create more difficult tasks, because you have to reprogram everything in all these codes. And so as we did a 4 experiment and trying to improve it, we said to ourselves, okay, let's create something that is fully modular, so we can define the complexity, and we can extend the task very smoothly, and we can create something you would like the neural network is capable to training more and more difficult tasks. And we said to ourselves, it also means we need the environment that is modifying according to the needs. So you start with a simple a reaching task, but then you need to transport something. You have to screw something, and it means more and more difficulty, but doing this programmatically. So we create this myGym toolbox that has to have these capabilities. That means it's modularity, procedurality for chaining the task. Real-time vision is good because you can do the sync to real transfer. So having a baseline is a good option because you can check whether what algorithms works and what not. And learnability, I will tell you what's learnability later. Okay, so at this slide I have to say, okay, all these toolboxes are not as good as our toolbox. Our toolbox is the best. Fine. What the modular scheme means, I mean, it's a whole architecture that everything is defined in the specific classes. So it's like a building a world. You have an empty scene, and you have a class that defines environment, and you can very easily create a world dedicating of a composing of the object with the increasing difficulty. So it's about the inheritance of a simple environments can inherit a more difficult environment, and everything is separated in specific parts of code. You also have an augmentation. You do have a vision module that you can use for a specific task, and then you can define the task. So this is what the modularity stands for from our perspective. If we started with creating this environment, that is where the tasks have so-called increasing complexity, because I mean usually it's all about that all the tasks are like handcrafted. It's all about like starting with reaching, then you have to pick something, then there is a throwing, there is a pushing, and then you can have a pick and place and a sequential task. But you can't measure a similarity between these tasks. I mean, there is no, like, you do have something like one parameter difficultiness level, but how to do this in environment? When you teach child, the child is able to create a difficultiness level by itself, but it means like having a system with the intrinsic motivation and other stuff. But we are still interested in this table desk task and that are predefined. But we copy the classical structure. I mean, there are many simulators that have like a 15 to 50 predefined tasks, and the similarity of the complexity and difficultiness level is arbitrarily defined. And so we copy that. I will show you in next few slides that we would like to extend this paradigm to something that is fully procedural and fully automatic. So the environment itself is evolving according to the needs of the robot or according to some inner curriculum. Okay, so we do have these predefined tasks in the recent version. We do have also because the task itself is defined by the complexity of environment somehow, and the complexity of the body that is behaving in the environment. So we implemented in a toolbox like a robots with less degrees of freedom up to the humanoid robots that have like plenty of degrees of freedom. That is also difficult for a neural network to be capable to control such a complex body, and also the state space of a solution is much more higher. But this is okay, like a second axis of that you can manipulate complexity, that you will train with more and more difficult robot, and it will tell you whether the algorithm is capable to pass through the thing. Now, how it looks like, also what are the advantages? I mean, we didn't find in the previous toolboxes is that we offer like something like a pre-trained vision. So you can have in any step of the simulation the visual model adopted. So you obtain, let's say, the RGB info from camera, and it will find you the object you are interested in case this is like a picking task. So it has to be the position of the gripper is identified in the picture, and position of the target object. So it will help. On the other hand, during the training, I mean, the recent systems that work in real time are able to reach, let's say, 20 to 30 frames per second. And if you know, when you train the stuff in a simulator, you can have like a 500 frames per second. So you can train very fast. The vision is the first bottleneck. It's well known that in a simulator there are two bottlenecks. I mean, to identify something on precisely in the environment, and second more difficult task is to grasp it, because the grasping itself, I mean, the vision, 3D vision, a good 3D vision is kind of art, and good grasping is sort of art. That these are specific sub areas. So right now we do have in simulator something that works like for 25 frames per second, and the training is very long. We also try to adopt there are so-called like a 6-dot vision. 6-dot vision means that if I look at the table, I know the position and orientation of the object, and then I'm able to grasp it. But if we apply these algorithms to the simulators or in the real robotics, it's still very slow, and even like a state-of-the-art stuff is capable to do, let's say, 5 frames per second. So the trading in a real 3D environment based on like RBG or RBGD cameras is still very slow. So this is one bottleneck. So we do have this solution that is somehow good. The second stuff we are also interested in is application of distractors, because we found that also like a difficultiness levels is dedicated to the stuff. That means that that can be distractors like a static ones that I have to avoid something. They have to be like they are what's the word for it? Predictable distractors, or you can have a chaotic distractors. In a later slide, and it's dedicated to the project we are starting with the beeping, is that the human-robot collaboration, because human can be considered as a distractor sometimes, but sometimes it's also like a task solver. And this is all again very difficult question: when the human is distractor and when the human is like a collaborator. So we at the present version of the toolbox, there are like these simple distractors, and the system knows about it, and it has to calculate. So the trajectories for doing the tasks are much more difficult together with distractors, because they stand for uncertainty of the environment. Okay. What is because these were all about the difficultiness as a spatial problem, but the most like a complexity and difficultiness of environment becomes from a temporal domain, because you have a task. I mean, like classical is how it's called. This is Tower of Hanoi. Tower of Hanoi is a classical problem. You have to do, you know to need the order, and you have to, the environment will somehow judge whether the order is complex. And this is where most of the simulators are, the simulators I mentioned are for something called single step task. Single step task is reach, pick, push, throw, and it works. We are able to train the network. But if you would like to train the network to, let's say, do the tower, then you have to specify it inside the environment, and then try to increase also the complexity. Okay, the second video is the second video is not working, but I will describe it. The first video is about the grasping. I mean, most of the simulators, the recent ones, work on the assumption that if I will reach the object, because the grasping is physically difficult, so it will magnetize it, and the object is, there is a simplification of grasping. And we try to research how to do this, and so we create a physical condition that there is a huge friction in the gripper, and we were capable, even with the neural networks, to grasp the object and hold it based on the physical properties. And then we also do the tricks like containment, so the gripper itself is able to contain the object, and then you don't need to calculate the grasp points. It's all about having the tricks that will not that will help you to solve the task in almost the real world, and somehow do the workaround about the real grasping. Oh, this is not visible. Okay. So the simulator nowadays looks like that you are able to define the environment, define the task, define the reward functions, also the robot body, randomization in one config file. So it will very easily help you to create a task with the increasing complexity. So it fastens our work, and we are able to test whether the algorithm, the reinforcement learning algorithms, are capable, or where they will stop. It's all about it. Okay, this task is easy, and now there is some breakpoint, and you are able to know the general capability of the algorithm to reach some level, and then you have to probably make some architectural design. Otherwise, the algorithm, it's like it's the roof, it's the top of it, and it can't go further. So in the toolbox, that is like a classical. These are the smell of the. These are like the visual types of the curves. So, but it's not visible. It's all about like a success rate and number of steps. The funny part we made is this that we call learnability. We try to visualize the general capability of the toolbox to work on a different task with the different parameters, with a different type of controlling. So it's like if you will create a grid and you train all the combinations, and then you try to visualize it not as a bar plot, but as an area. So if the algorithm is like generally capable to work on all tasks, there will be there will be all the area covered. So each dimension stands for one combination of training, because we were interested in having a general capability to learn the curriculum as one number. So this is like just a mathematical simplification of the learning progress. Okay, there is a documentation. This is just like that the toolbox is like treated well, and we take care about our customers. And this is like a present status, and I will show you what is like a work in progress, the stuff we didn't finish so far, and there will be probably the goal, some goal of the project. The first one is to having a human as a distractor and a collaborator. So right now we do have just a random bubbling of the human body. So at the first stage we would like to add the virtual reality support. That means that you can behave together with the inside the simulator. Robot is able to learn, and you are able to provide the other input as a distractor or as a collaborator. So it's about the technical stuff that you will somehow manage the data flow from a virtual reality headset into the simulator and the ability to use it. So this is the first work in progress stuff. The second stuff, it's near the publishing, because we realized that all these algorithms, when we sequence the task, you can like building a tower. For one network, the one neural network is not capable to do such a stuff, because there are so many, the tasks are diverse. You have to pick something, you have to put somewhere. Yeah, maybe you can rotate it. So the recent progress working with just one network that is not capable to do the long horizon task. Our contribution is that we are for each subtask there is a specific network. It's like creating the expert. So I do have an expert for reaching, I do have an expert for grasping, I do have an expert for placing, I do have an expert for rotating, and we are able in this version of the toolbox we are able to create, let's say, 3 or 4 network versions where the networks are switched in a specific point, and they are capable to do a very difficult and very complex task. And as you see the graph, the gray one is when you use just the one network for all the sub goals, and the colored one are when you use the several networks, each specified for each goal. We consider it as a fruitful idea, and it should continue to do. Then we are moving to something that is in artificial intelligence called like a planning problem, that you have to order the sequence of skills together to be capable to do very, very complex tasks. And these networks are just these skills, and then there has to be other algorithm that is capable to chain them. And what we consider as the most difficult task is to find a place when one skill is finished, how to recognize it, how to define it, and switch to another. Yes, so the chaining and also find these crucial points should be interesting, because when the neural network will be capable of this, then there is like a fully neural network-based architecture that is capable to do long horizon tasks, and this is also like very desirable in also in our industry. So Nowadays, these are just like a very simple, like a stacking task, but compared, I mean, to the state of the art, this is, I mean, we reach the accuracy that is better than the classical single network task. Ooh, does it work or is no, yes? Can we run the video?
Maybe change.
Or maybe you can find it on Google. So this leads us to the conclusion that was proved. I mean, I think it's 1 year ago, the Google created like a generally capable agent in this simple world. And the generally capable agent stands for, if you create environment where you can procedurally generate the task, I mean, and you know the similarity between them. So it's like because what I showed to you was the like a pick, play, push, throw task, but you don't know what's the let's say now distance between pick and between place, because you don't have like such a space for it. But I mean, at the Google, they work hard on this environment that they look like maybe like a Minecraft world, but they are constructed procedurally with, you have like 5 or 6 parameters that stands for a difficulty, and you can create like, let's say, thousands of tasks. They are not sensual, but for a human, but they, you know, the similarity between them because they are parametrically driven. So it's like creating the curriculum. Developmental psychology will tell you, okay, there are stages of it. First is this, that, but the idea is to having these like ability to mathematically define the difficultiness level. And our goal, or what is work in progress now? Okay. It works so that there is a, let's say, grid world, and then there are some arbitrary tasks that capture the flag or put something on the place or go higher. And this is similar to robotics task, but the agents are different. What was the idea? They created this environment, this Xland, and trained these agents. And then they give them like a meaningful task, like capture the flag, whatever. And the robots that never saw such a task, based on this curriculum, like a huge curriculum training, were capable to solve the task. So that was something like a general knowledge, or they trained the general knowledge. And where was the trick? It was about the continuous environment that is that complexity is defined, precisely defined. This is what we would like to put into the robotic task, because this is like, if it works in this agent world, it has to work in the robotic domain, and it's all about, I mean, the code of the agent is publicly available. The code for the environment from Google is hidden. Maybe the code for creating environment is much more difficult, and they don't wanna like publish it. But we do have some basic ideas how to do this in this manipulation task, and we do have also some ideas what parameters should be interesting to define the complexity of the task. Training a neural network well, from my perspective and from my experiences, consists mostly of having a good data, my colleagues say data set, having a very good environment, that are pretty scalable, and also having a good task. But the task itself is somehow, it's tricky moment, because you can have a very complex environment with tons of objects, but the task will be like go to this position, yeah? And the complexity of environment is, let's say, 100, but the task itself is super simple. So you have to also define the complexity of the task. This is what we are working on also right now, and also define it somehow mathematically or programmatically. But whether the task is valid, because you can train a pick and place task, and you will reach, let's say, 70% accuracy, but maybe the 30% is that you just sampled the object out of the robot reach, but you didn't mention it because you just You just define it. So it also for us to know that all the tasks we are presenting for a system are like valid. That means to have their analytic solutions. I know that the neural networks are sometimes capable to find a non-analytical or the solution that is not obvious, but okay, let's also define the difficultiness level of the task based on that you are creating the task, you are validating them, and the video is all about that you do have a random sampling object, and the robot analytically is like creating the paths, whether he's capable to grasp it, whether he's capable to move it, and when it's valid, he said, okay, this combination object is valid. And this is also like a desirable for having a control about the complexity. So what I'm talking about all the time is if you do have a fully controlled environment and fully controlled task, maybe you can also to push the limits of the neural networks that will fulfill this task. Okay, and this is the video again, and this is and it doesn't work, but this is just the overview. Okay, what's the take-home message? I mean, from this, I summarized it like 10 seconds ago. It's about having a good curriculum or knowing the similarity between tasks that will help you to improve the quality of these controlling mechanisms behind the robotic manipulation, and maybe also but this is just a hypothesis. Having a special neural network strength for specific subskills can also improve the quality as each network is just used for a specific task. And yeah, to sum up, we would like to use the part of the simulator as a part of the project that we are starting right now. That's why I chose the topic to let the partners know what's the idea behind. I think it's all. Thanks for your attention.